Yes. So, hi everyone. Welcome to the Good Vibration Seminar for this ninth seminar of the second year of existence. So, I'm very happy today to introduce you Pierre Houdayer, who is doing his PhD here at Paris Observatory. So we first noticed Pierre during his bachelor. He was studying in the University of Rennes, and he was being taught stellar physics by Evelyne Le Breton. And so that's when she noticed him, and she brought him to the attention of the colleagues here at LESIA in Meudon. At the end of his bachelor, he did his thesis at LESIA, and that's when the collaboration mainly with Daniel Rees and Marie-Jo Goupil started. So that's when he became first familiar with glitches. And then he continued in Paris Observatory for his master's, where he had excellent records. He was ranked first and second, or the other way around in the master here. For the first year of his master's, he did his thesis on distortion of 1D models into 2D, accounting for centrifugal acceleration. And he was supervised for this work mainly by Daniel Rees, but also Marie-Jo Goupil. Second years of master, he started more or less his PhD project by studying glitches due to the helium ionization zone. So mainly his work consists in theoretical developments, which allow to describe the profile of the first adiabatic exponent impacted by the helium ionization zone, and mainly building a sort of a physically motivated model which doesn't require ad hoc profile of gamma 1, basically, so which would not require calibration. So he will talk about this more, of course, in a minute. Just to conclude on his introduction, he already has one published paper and has another one in preprint. And he will be he is actually looking for a postdoc, and he will have his PhD this autumn when he will be ready to start the first postdoc. So thank you very much for being here with us, and I think it's time to give you the floor, Pierre, for your seminar.
Thank you, Rita, for introducing me. So I will share my screen. Okay, do you see it?
Yes, perfect.
Okay, so good morning, everyone. So I'd like to present a few results about the determination of helium abundance by exploiting the ionization glitch. So most of the things I will present and figure I will show can be found in 2 articles. So the first one has been published last year, and the second one has been submitted last week. So now I will start with the beginning. So first question to ask is why looking for an helium estimate? So a figure I'd like to start with is this one. Can be from the work of Evelyne Le Breton and Marie-Jo Goupil. So it shows multiple estimates of the mass and initial helium abundance for one single star, considering both spectroscopic and seismic constraints. So the reason why there is multiple estimate for one single star is because the study sought to consider multiple possibilities about the internal physics. For example, changing mixing length, diffusion model, opacities, and so on. So, of course, by doing that, we increase the uncertainty on both parameters. But you can see that this shape, this degeneracy between the mass and helium, make the result way more uncertain because of the insufficient knowledge about the internal physics than the imprecision if we look at the individual error bar. So in this particular context, you can see that having somehow an independent estimate of helium, and so expressing it in terms of the initial helium abundance, would have a double benefit. So first, you can see that the uncertainty on the mass is way smaller than. And the second benefit is that you can see that we can discard, or more precisely make less plausible, the physics of the internal models that are outside of this range. So now, having said that, the question is how to obtain such an helium estimate. So a good idea is to look at the contribution of helium ionization. So here I show you the first adiabatic exponent near a star surface as a function of the acoustic depth, which is just the time it takes to the sound to reach a certain point in the star. So this exponent has typically as value 5/3 in a convective region. But here you can see clear deviation from this value caused by ionization of hydrogen, the first helium ionization and the second helium ionization. So each one takes the form of a well. And so the good news is that this signature is actually visible in the oscillation frequency. So we can model this signature as some deviation of the oscillation frequency caused by the ionization. And we call this deviation the ionization glitch. So here I will try to present a very general procedure to exploit it. So the first step is generally to consider a perturbation model, like this one, P. So we just saw that the deviation caused by ionization takes the form of a wave. So here I represented a Gaussian shape, but we could consider a different model. And then we will trying to answer what would be the signature of this perturbation in the oscillation frequency. So usually we do that by considering some theoretical developments. Typically, for this perturbation, we can expect some sort of damped oscillation with a certain period. Then, if we have data, if we measure an actual deviation of the oscillation frequency, we can fit this signature to obtain constraints about the internal structure, and so best parameters for the model. So that's for the general procedure. So now I'd like to raise a few key points about this procedure that will serve as guideline in this presentation. So the first question we can ask is how to choose a model for the perturbation. For example, here we proceed kind of visually, but can we do something else? Is there a more legitimate model for the perturbation? Then I said that I wanted an independent helium estimate, but here you can see that we find some parameter of a Gaussian, which is not directly the helium estimate. So is there a more direct way to find this helium estimate? And then the last point concerns the model of the glitch. We will see also that there is multiple ways to do that, so we'll try to review that. Okay, so I will start with the first step, that is modeling the structural perturbation, so the model P we just saw. So for that, I considered a thermodynamical framework that corresponds to an ionization region inside the convective zone. So here you can see the different hypotheses I use. So for example, I considered isentropic region, uniform abundances, the chemical equilibriums that correspond to ionization, and of course, electron neutrality. So from there, we can derive an analytical expression for the first adiabatic exponent. So in the case we deal with a mixture of only composed of hydrogen helium, we can end up with a formula that depends only on the density, the temperature, and here we represent it for a typical helium fraction. So we can see this map kind of 2D version of the profile I showed earlier. For example, you can see here the deviation caused by the second helium ionization, here's the first helium ionization, and here's the hydrogen ionization. So it gives a nice figure, but for now, it's not completely a model yet. For that, we need to consider a structure. And we can obtain that by considering the balance between the hydrostatic equilibrium and Poisson's equation. That will impose a stratification for the model. And then a certain relationship between the density and temperature. And so then along this line, we end up with a complete model of the structure. So we can look at what we obtain with this model. So the model we found is found to depend on 3 parameters. So an interesting point is that it's not parameters we introduce, it's more like dimensionless quantities that have an important effect on the model. So it's more like it emerges from the equation. So the first parameter is the helium abundance near the surface. The second parameter is a thermodynamical quantity, which is the electron degeneracy in the convection zone. And the last parameter is a parameter that impacts the extent of our ionization region. So here you can see the impact of on our first adiabatic exponent, gamma 1, as a function, so this time on the normalized acoustic depth. So for example, we can see that changing the helium abundance will increase the depth of the well, which was kind of expected. If we change the electron degeneracy inside the model, we can see that it impacts the dispersion of each well. For example, at low degeneracy, we will have very localized ionization well, while at high degeneracy, all the wells seems kind of merging altogether. And so the last parameter, just apply a factor on the axis, you can see a dilatation. So this model is really useful if you want to find a perturbation, a model for the structural perturbation, because we can only take the difference of 2 models we just saw, and then we obtain a model of the perturbation for the change in parameters between the 2 models. So for example, here you can see the impact on the structure that have a change in helium abundance and of the other parameter. So you can see that we obtain some elaborate shape. You can say it's more complex than the Gaussian well, for example, we represented in the introduction. And also in the more general case, we would have to consider multiple perturbation on perturbation on multiple parameters at once. So we can end up with even more complex profiles. So that's for our perturbation model. Now, if you want to relate that to the oscillation frequency, what we can do, since the perturbation model is defined as a difference of 2 models, what we can do is compute numerically the oscillation frequency of both models and then take the difference. So then we obtain a glitch, the signature in the oscillation frequency caused by a certain change in parameter. So here we take 3 examples, 1 for each parameter, and we obtain 3 glitch. So I just precise that the glitch here is expressed in terms of not on the frequency, but the normalized frequency, so normalized by the acoustic radius. So we represented the glitch for a lot of frequency, as you can see, and for low degree modes. And the first thing we can observe is that the ionization glitch doesn't seem to really depend on the degree of the mode. They all seem to follow the same relation. So a second point also is that we obtain an oscillation as expected, so caused by the helium ionization, but not only. We have also some sort of slow trend for each perturbation. And actually, if we look at the structure, this slow trend is caused by the beginning of the hydrogen ionization each time, this sort of peak in the structure. So I will refer to that after as the hydrogen components. So of course, having said that, the question is more, is it possible to go the other way? Like if we observe a certain glitch, is it possible to retrieve the change in properties in the ionization regions that caused it? And so for that, we need to model the glitch. So that's our second point. So for that, we consider also a theoretical framework that corresponds to studying the oscillation of radial modes in an isentropic region. So the reason we consider radial mode is because we just saw that the glitch doesn't seem to depend on the degree of the mode. So both this hypothesis cause the lamp frequency and the Brunt-Wasserler frequency to be both zero. So that the only characteristic frequency we end up with is the cutoff frequency. So of these expressions that we express in terms of a normalized frequency scale. So from there, we can obtain a rather simple wave equation that relates the displacement caused by the oscillation to the oscillation frequency itself. And you can see that this wave equation then only depends on the cutoff frequency. So the cutoff frequency we represented here as a function of the normalized acoustic depth. So you can see, for example, that for a fixed frequency, this cutoff frequency only determines the propagation regime of the oscillation, if it's evanescent or if it's propagate. Also, another thing we can see that this cutoff frequency actually contains the signature of ionization for hydrogen and also for helium. So since we are interested in describing the glitch, we can try to express the perturbation of the frequency from this formula. So to do that, we can only project this equation and then disrupt it. And we obtain a rather compact expression for the glitch caused by a structural perturbation, expressed as a function of the perturbation on the cutoff frequency. So at this point, we can sum up. So first, in the first part, we obtain a way to relate some change in properties to a change in structure inside the ionization region. And then here you can see that we obtain a way to relate a change of structure to a change in frequency. So what we can do is combine those two relations to end up with a formula, what I call a glitch model, that relate directly a change in frequency to a change in properties inside the ionization region. So here, delta theta is just a more compact way to express all the perturbation in the model. So what we can do is to compare the formula we just obtained with the numerical glitch we computed earlier for each perturbation. And you can see that we have a good agreement between both formula clearly. And we can, so the formula is able to recover the oscillation caused by the helium glitch, but also the slower trend, not only the oscillation. So now we will try to retrieve the ionization properties from the glitch, which is kind of considering the inverse problem. So to do that, we will consider again a numerical glitch to create synthetic data. So the advantage of doing that is that we can create data knowing what is the correct change in parameters. So it creates kind of a framework where we know what is the true solution. So we can assess how well or bad the model is performing. So for example, here you can see the change in parameters we consider to create the data. So if you remember, the value is just considering all the perturbation we saw earlier at the same time. And you can see here the synthetic data we produce from that. So of course, we largely reduce the number of frequency we considered. we only consider here radial mode, and we introduce error bar from a very basic noise model. We simply consider white noise on the frequency. And so from that, we can do a fit. So we considered a Bayesian inference to infer the parameter by using the model we just introduced. So on the right-hand side, you can see the distribution we retrieve on the parameters, with the true solution being these black lines. And on the left side, you can see the value of the model for the most probable value inside the distribution. And you can see also some curve randomly chosen from this distribution to see what dispersion we obtain. So there is a few things to notice about this distribution. So first, the true solution seems to be in the correct range comparing to the value we retrieve, even though each time we underestimate the value of each parameter. The second thing to notice is that we don't have the same extent on for each dispersion on each parameter. For example, you can see that the value of the extent of the ionization region is more constrained than the value of the helium abundance, for example. So a reason for that can be found just below. So you can see we end up with a really strong degeneracy between the helium abundance and the electron degeneracy inside the ionization region, mostly because they produce kind of similar behavior inside the structure itself. So a question we can ask is that considering the comparison between the numerical glitch and the model we saw earlier, that were really similar, why don't we obtain a perfect retrieval of the parameter? So a thing we can look at is that a lack of information, especially considering the slow trend, the hydrogen component of the glitch. So for example, if we do the same exercise, but this time we add additional low frequencies at the beginning of the glitch, and if we redo the fit, then you can see, so here in gray, it's old distribution, so the one we just saw, and in blue, it's a new distribution with the additional low frequency. So you can see that all our estimates drastically improved. Like we almost end up with a perfect retrieval. You can see that the correlation between the parameter at the bottom disappeared. We have no correlation anymore. And you can see that, however, the degeneracy is still there because of more deeper meaning inside the structure. So you can see that it greatly improve the retrieval. And the reason for that is that because we gain a lot of information by doing that on the slow trend of the glitch. For example, if we do the same exercise, but adding higher frequency instead of lower, the distribution wouldn't have changed at all. So now a last point I'd like to cover in this presentation is how to handle an additional contamination to the glitch. Because of course, in the practical case, we do not observe directly the ionization glitch alone, but we can observe contamination, for example, from another glitch or from surface effects. So there's usually two ways to deal with that. The first one will be to use a diagnostic, for example, a combination of frequencies as the second differences to eliminate the contamination. And the second one will be to directly consider the frequency, but introducing a model to handle the contamination. So I investigate both approach in the article, but here, because of time constraint, I will only focus on the second one, using the frequencies directly. So we can consider the example where we have, in addition to our ionization glitch, contamination by surface effect, for example. So by doing that, we have new data. So you can see here our old ionization glitch in blue. And in red, we have the additional surface effect that we introduced by using an ad hoc formula from the work of Takafumi-Sonai. And so in black, you can see the total synthetic data we expect from the sum of the two contributions. So to deal with this problem, we have to introduce another model, a model of the surface effect, so parameterized by a certain vector here, mu. But we have two constraints on this model because we already have information about the surface effect. For example, we know that the surface effects vary on large scales, and also they become more important as the frequency increases. They are very low at low frequency. So we could consider a lot of models to reproduce these two behavior, for example, polynomial. But here I want to focus on result I obtain by using a Gaussian process to model this surface effect. So I don't have much time to go in the theory of Gaussian process, but we can see in process like an extension of the notion of distribution to the function space. So for example, we can draw a number from a distribution and we can draw a function from a process. And so here you can see a sample of function we draw from our process we use to model the surface effect. So of course, in this sample, you can see that many curves doesn't correspond to realistic realization of the surface effect because it's sample for the process a priori. So in those curves, we can see interesting behavior. So for example, we can see that we indeed have a low amplitude at lower frequency, and the process seems to vary on sufficiently large scales. But also we have very flexible behavior and only for two parameters. So now we can look at what we obtain by fitting the synthetic data on the left by our new model, the sum of the ionization glitch at the Gaussian process. So in terms of the distribution on the parameters, so yeah, I will only focus on delta theta, mu is the parameter of the process. So we see that we still retrieve relevant information. So of course, the extent of each distribution has increased because we have the same amount of information that we distribute on 5 parameters instead of 3. But we still are in the correct range of the retrieval. So most of the loss on the of information concern the extent of the ionization region, these parameters. So on the left, I represented the fit with the function. So again, the most probable function according to the distribution and a random sample for each component. So you can see that our model fits really well the data we introduce. But what is more interesting is to see what it predicts about the component it doesn't see, like the ionization glitch. So you can see that we retrieve the correct shape, but with slight offset, mostly because you can see that we have a slight undershoot of the process to model the surface effect. Okay, so I think I will stop here. So just I give you a quick summary of the point we see. So the first step was to derive a model of the ionization glitch, and we did that by considering a thermodynamical framework. So an advantage of the model is that it is directly able to provide information about the ionization region properties, and we don't have to do calibration, for example, using realistic stellar model for that. So considering the glitch, we saw that the glitch is composed of two components. So the first components that vary on large scales, that is due to the ionization of hydrogen, and the faster oscillation due to helium. And we saw that this component actually contains a lot of information, even to constrain the helium abundance. And so at the end, we saw how to combine this model with a Gaussian process to handle the case when we have additional contamination. And so, of course, the prospect of this work is to now apply this method on actual data instead of synthetic data, for example, the Kepler legacy sample. So thank you for listening. And if you have a question now.
Thank you very much, Pierre, for a very interesting presentation. I think you only slightly tackled some subjects that we now have time to dig in, if you want. So if you have questions, do not hesitate to raise your hand. Of course, we encourage young researchers and colleagues to go ahead. So first of Martin, go ahead.
Hi, Pierre, can you hear me?
Yeah, I can hear you. Hi, Matt.
Good. It was really nice, thank you. And I just have one or two questions, I don't remember, which are about the models mostly. So from what I get, you derive perturbations of the frequencies upon perturbations of the models. I mean, isn't it right? Or sort of?
So what I did is to derive, so here you can see perturbation of the structure.
Yeah, that's right.
And so again, so then we derive a formula to express how a change in structure impacts a change in frequency through the perturbation of the cutoff frequency. And so then we just complete the line by considering how then a change in parameters impact a change in frequency.
Exactly. So that's my question. So in the end, what you get from measuring the perturbations is a perturbation in the, for example, helium value, but don't you need a reference one if you want to apply to, let's say, observe data? Because
yeah, of course, yeah. Yeah, you need a reference structure to infer the helium value, because you will measure a deviation from this reference.
So you would need some sort of calibrated model upon data. I mean, upon the let's say non-glitch indicators held by the frequencies, isn't it? Or
yeah, you only need, for example, say you can take a model that approximately corresponds to the data. So for example, in terms of seismic observation. And then you can try to correct the value of helium abundance by trying to fit the change in frequency to infer a certain change in helium, for example.
Okay, that's cool. So it's sort of an inverse seismic modeling of the glitch rather than the more forward approaches we have now.
Yeah,
if I could say.
Actually, the way it's formalized is really close to some kind of inversion with a really low basis, really low number of basis functions. So.
Okay, that's nice. So you would need a start model, but in the end you could get maybe more precise inferences. And so the second thing that I was curious about is, as you get frequency differences between different models, sort of, isn't it these differences also should hold information about the glitches? What I mean is, you have the frequencies you compute already have glitches, isn't there? And so you get differences between frequencies which already have glitches.
Yeah.
Okay.
Yeah, you don't have to assume that the reference model doesn't contain any glitches. So you don't have to assume that your reference frequency have to be smooth. You can
So
measure difference between.
Oh, sorry. So don't you suppress part of the glitch information in doing so?
What do you mean?
I don't know. Maybe if you have two, let's say, models which are slightly different from one another but have mostly the same slow frequency varying trend or something, wouldn't you cancel out those?
I mean, if the signature of the glitch cancel out, so basically, so of course, at first order, you can consider that both your model actually don't differ in the ionization region, so that they don't have a change in properties between the two of them.
Yeah. So yeah, true. Okay, thank you.
Thank you. We still have plenty of time for questions. So go ahead, Jörn. Can you hear me?
I'm coming. Here we are. Thank you. Of course, I do feel very young. So thank you, Pierre, very much for a very interesting talk on the subject that, of course, I've been thinking about a bit. And so I've got several questions here. First of all, it's unusual to talk about degeneracy in the in the convection zone.
Yeah.
So what is the physical reason for this fairly strong effect on the gamma-1 bump from the degeneracy parameter?
Yeah. So actually, if you look at the value I show for the degeneracy, so degeneracy is expressed as the logarithm. So you can see that is every time very small value. So of course, the electron degeneracy, whatever the model you consider, is very slow inside this region. But yes, clearly it has a strong impact on the ionization.
Yes, I see that. Maybe just to set the scale, do you know what a typical value would be in the solar convection zone?
-5.
-5, okay. But what's so this affects the Zaha equation somehow?
I'm sorry?
The effect you see in gamma-1 must be an effect on the ionization process.
Yeah.
So how does this enter into the ionization process?
So this electron degeneracy parameter appear inside the psi equations. So you can express the psi equation. So you would have the exponential minus the potential over the thermal energy, and then minus the degeneracy to that.
Yeah, sure. Okay. That's very interesting. I should know that because I used the EFF equation state where that directly uses that technique. So 50 years ago almost. So yeah, that's interesting. I should look more at that. But then the second question, you have this strong degeneracy, between the helium abundance and the degeneracy parameter. But I would assume that when you are fitting data to models, other parts of the fit would give you quite strong constraints on the degeneracy parameter. And so maybe you could get around that. I mean, if you know the radius of the star, for instance, you would have some idea about the structure of the convection zone, and therefore also about the degeneracy parameter in the convection zone.
Yeah, so of course, yeah, you would have some quite strong constraint, but here, if you look at the change in the value of the degeneracy parameter, you can see that it's a few tenths to consider a change in helium to also almost 1/10. So actually, you would to raise this degeneracy, you would have to have really strong constraint on the electron degeneracy parameter, I think. Yeah.
Well, that of course is something you look at when you go analyze the legacy data, because you have to take into account all the information in the fitting. But of course, I agree that we need to constrain the helium abundance to make separately, to make good fits to the data. Also, I was very impressed by how well your, I would almost call it toy model for the glitch frequency effect fitted the calculated frequency differences.
And this one.
Yeah, that's right. So the red curve was calculated from your isothermal model.
Yeah.
And the points are calculated from realistic realistic models, I guess.
Yeah, yes, it's from, we computed numerical frequency and took the difference.
So, but of course, your time model looks very much like the real life if you think in terms of an equation for the oscillations of similar form. So that it does make some sense. Okay, well, thank you. This is very interesting.
Thank you.
Thank you. So I don't know if anyone else would like to know more about helium glitches. It's time to ask Pierre. So I see that we don't have any more questions. So I think it's time to thank Pierre again for a very nice introduction of his work. More to come in the paper here, which is in the preprint. You can already, I think, have a look at it on arXiv. Well, thanks a lot to everyone for joining us again. So next time the seminar will be given by Arthur Lesaut from University of Exeter. I think you noticed that we now are on a cadence of once every month. So we will meet on March 16th at 10 a.m. for that meeting, for that seminar, and it will be on two-dimensional simulations of solar-like models with enhanced luminosity. So thank you very much, everyone, and I hope to see you all in a month. Thank you again, Pierre.
Thank you.